Atmospheric moisture. First of all, let's look at the visuals. There we go, atmospheric moisture. Visuals, clouds, readily visible. More atmospheric moisture, steam, again readily visible. And indeed, atmospheric moisture coming out on frozen glass. However, there's atmospheric moisture here. Where is it? We have to make it visible to actually see it. How do we do this? By measurement. That is, by producing certain data. So let's first look at relative humidity and vapour pressure. Temperature and relative humidity. At 10 degrees, the air can retain a maximum of 7.5 grams of water vapour per kilogram of dry air. Double the temperature and we roughly double this. So the warmer the air, the more water vapour that can be resident. However, it is important to know how saturated the air is with water vapour, and this is what we call the relative humidity. It's a measure of saturation. Broadly, we can say the amount of water vapour in the air at any given temperature, expressed as a percentage of the maximum amount of water vapour that can be resident at the same temperature, is known as the relative humidity. Therefore, note that relative humidity is a proportion. It is not what one could call an amount. So what are the effects of cooling air on relative humidity? Well, let's imagine the air as a bucket, okay? The warmer the air, the bigger the bucket. Conversely, the colder the air, the smaller the bucket. And so we start off in our hypothetical case here, 20 degrees, biggest bucket, 60% relative humidity. That bucket is containing 60% as a proportion of its volume. What we're going to do now is cool the air, and we're going to cool the air down to 15 degrees. The bucket gets smaller, but we're going to pour that amount of material in the left into this bucket. Same amount of material, but this time the relative humidity has increased to 83%. Why? It's simply a proportion of the volume of that bucket. We're going to cool the air down again. We're cooling it down to 12 degrees. Bucket gets smaller. We're going to pour the same amount of material into the bucket. Our bucket is now full. We're going to cool it down again, of course, to 10 degrees. So what will happen if we pour that amount of water on the left into this much smaller bucket? We're going to get overflow, and basically at that temperature the air can no longer retain the water vapour in it, and it comes out. That is where we get condensation. And indeed, a decrease in heat increases the relative humidity, not the amount of water but the proportion. Similarly, an increase in heat decreases the relative humidity. If we look at surface condensation, this is just simply a principle. The figures aren't actually spot on by any stretch. Let's start off by looking at a cold wall on the right. We have a relative humidity scale there and an air temperature scale. Now here we are looking at what one could call the boundary layer of air. This is the air that is literally in contact with the surface. So we start off in our hypothetical case with air somewhere in the order of 17 degrees and a relative humidity of 76, 77. However, as that air really does come into very, very, very close contact with the wall, it's being cooled, our bucket is getting smaller, and at say 15.5 degrees we have the relative humidity increased to about 88%. And as the air gets cooler and cooler, following the red line down, we get to a point about 14 and a bit degrees where the air can no longer retain the water in it. It's reached 100% relative humidity. This is known as the dew point temperature. And at this temperature, the air is fully saturated. Any more cooling and the water must come out of the air can no longer retain it, and we get condensation form. And it is important to understand that the dew point temperature is where 100% relative humidity occurs. So you're sitting in your office and somebody comes along and says, look, I've got these figures, 60% relative humidity in the room on the left and 70% on the right. Which is the dampest room? The answer is you don't know. Why? It may be purely a temperature effect. Relative humidity is affected by temperature. And again, another hypothetical, or rather just telling us the principle, changes in relative humidity in a property, say in the winter. And there's our property, insulation, timber suspended floor, and we measure a temperature of 20 degrees at 44% RH. It has a vapour pressure. We'll mention this later, give more details, but vapour pressure actually reflects the actual amount of water retained in the atmosphere. So the air moves up and down and round and round, and some of it will get beneath the floor, assuming no ventilation. It's cooled to 13 degrees, so what will happen? Smaller bucket, the proportion increases, so we now finish up with 69% relative humidity. Vapour pressure the same amount of water vapour in the air. And similarly, in the roof, we finish up, it's cooler again, and we get 74% relative humidity, same amount of water in the air. Looking at the external atmospheric conditions, the relative humidity, this is taken from British Standard 5250, 2011 and 2016. Just looking at relative humidity alone, notice in the colder months of the year, the relative humidity that one might expect on average is over 80%. The relative humidity is over 80%. And this will play a part sometimes in some of the ventilation. And again, relative humidity in a roof void and the external levels in the winter. These figures initially suggest a well-ventilated roof. Why? Because the external air is potentially sweeping out any internal air, and therefore they are very, very similar. The external conditions will be reflected internally in this roof void. But to nail this right down, you need other data. And again, similar effect in a subfloor void. The external in winter suggests that it's well ventilated. Very, very similar RH conditions. The external conditions are being reflected in the subfloor void because the air is sweeping through, and you're getting the same air effectively in the subfloor void as you are outside. But again, to confirm this or make other adjustments, you will need to have more data, the temperature data. Water vapour moves. Why? It exerts a pressure and will move down its pressure gradient. So, in the colder months indoors, there is more water vapour within a property. Why? Well, it's generated by occupation. So we've got more water vapour in a property than outside, and therefore it will move down this pressure gradient. It moves out through cracks and crevices and windows, but it also moves through the fabric of the building itself. But this is extremely slow. And if we look at why it's extremely slow, we can look at these figures. Vapour resistivity. The higher the figure, the greater the vapour resistivity. Look at the vapour resistivity of stonework. Very high to infinite. But notice the vapour resistivity of air is 0 and mineral fibre is absolutely minor. The other feature to bear in mind about these resistivity figures is that they are additive. So if we have 2 or 3 of those materials on top of each other, then we add them together and get far more vapor resistivity. We've had a look at surface condensation, but we also come across interstitial condensation. This is where the dew point is reached within the fabric of the structure. And there are 2 diagrams. Surface condensation in the top diagram is forming on the surface, and in the lower diagram, interstitial condensation. In this case, it shows it in cavity walls. In essence, is it really interstitial condensation, or rather just condensate on the surface of the outer leaf, or the inner surface of the outer leaf? But you can get it in solid materials, permeable solid materials. If we look at this, there's a wall temperature gradient going through a wall. But we can also calculate a dew point temperature gradient. Remember, dew point is the temperature at which condensation will occur. If the wall temperature gradient drops below the dew point temperature gradient, then we will get interstitial condensation. Interstitial condensation is most likely to occur where there is an external vapor check, which will even slow down or prevent the successful passage of moisture-laden air out through the wall, such as dense renders, impermeable finishes, and usually where there is a high internal moisture production. Well, interstitial condensation is not actually measured. It's usually the risk of it occurring that is calculated. It's not usually physically assessed. But we need to know the precise structure of the, let's say, a wall, for example. Once we know this, we need to know all the details about the wall, thickness and materials. The risk of interstitial condensation can be calculated. And data on vapor resistivity, thermal properties of materials and so forth are given in the British Standard below and a Building Research Establishment Digest 110. And what we finish up with is what we've just seen, and this is by this wall temperature gradient, dew point temperature gradient, and indeed where they cross, then theoretically there is a risk of interstitial condensation occurring. So we can summarize the following. Relative humidity is a proportion. That is a measure of saturation. It's not what one would refer to as an amount. For a given level of moisture retained in the air, the relative humidity will change with temperature. A high relative humidity does not necessarily reflect a high level of retained atmospheric moisture. It's temperature dependent. And we can go a little bit further and look at water vapor and vapor pressure, and put these into perspective in relation to relative humidity. Water vapor, as we mentioned earlier, exerts a pressure. That is directly related to the amount of water vapor retained in the air. The more water vapor, the greater the vapor pressure. In other words, it reflects, or it's a reflection of the level of water vapor retained in the air. Vapor pressure is not proportional to relative humidity. Why? Because relative humidity is temperature dependent. Therefore, for practical purposes, vapor pressure is not. It's measured as grams per kilogram of dry. So, if we look at these together, on the left we have our example of relative humidity as a proportion. But if we look at the example on the right, we can change those into, for example, vapor pressure. And just for convenience, we've simply called them units. So the one at the top now becomes 2 units, it's a measure, and the one at the bottom is now 1 unit. With reference to vapor pressure, it doesn't matter how big, for want of another words, the bucket is. Because if you took a 50-gallon bucket and put 1 litre of water in it, you've got 1 litre of water in a 50-gallon bucket. Double the size of the bucket, you've still only got 1 litre of water in it. And moisture production per day, average dwelling 4 to 5 people. Well, where they are, here we are, some figures. Total 14 to 17 litres per day. The only one I have disagreements with, or rather questionable, is washing clothes. I don't think that much water would come out of a washing machine. However, there we go, a family, 14 to 17 litres per day. Indeed, an individual can produce up to 9 litres per day. And we'll see this later on. So you'll now ask which is the dampest room, one on the left or the one on the right. Well, clearly the one on the left is. There is more water vapour in the atmosphere than there is in the room on the right. Going on with our water vapour, UK external atmospheric conditions vapour pressures. We've looked at humidities, but here are vapour pressures. This is the actual amount of water vapour that one would expect in the air. Note, there's a lot less during the colder months of the year than there are during the warmer months. Indeed, we can get down to 0.5 kilopascals, much lower on really cold, frosty days. And again, the external air temperature and vapour pressure. Again, in the winter, the colder it is, the lower the vapour pressures. The warmer it is, the greater the external vapour pressures. The other feature of water vapour, of course, it exerts a pressure. We mentioned that earlier. But it moves, therefore, down its pressure gradients. Let's take, for example, a kitchen. A lot of water vapour being produced in our kitchen. May not show up really, a bit of condensate on the windows, but it doesn't really show up because of the conditions there. However, it will follow its pressure gradient, and it can move around the house to areas of low vapour pressure. They may be significantly colder, and one finishes up with a problem well away from where the water vapour was developed. Indeed, you'll also find that wind direction will influence the movement of water vapour in a property. If we look now, carrying on with our water vapour, at internal and external environments, in an unoccupied house there's roughly the same level of water vapour in the property as there is outside. It comes into equilibrium. There's no water vapour being developed anywhere. There's a little difference in the vapour pressures between internal and external moisture levels. And one's got to remember that the total water vapour internally is the sum of internally generated water plus external water vapour. That is a sum. So we've got the external water vapour added on to what is generated internally. Hence we have more water vapour internally than externally in an occupied building. Again, considering internal and external environments, as mentioned earlier, almost all the excess water vapour in an occupied building comes from occupation activities. And during the colder months, there is inevitably more water vapour in a property than outside. There's less ventilation. Windows are closed, doors are closed, etc., etc. So, there is a difference, therefore, between internal and external moisture vapour levels. That is, internal minus external. This difference is very useful, and it is known as the differential or excess vapour pressure, and it reflects solely, this difference, the internally generated moisture, because from the internals we're taking away the externals. And one will find on cold winter days there's usually less water vapour externally, we saw that earlier, than on warmer days, and that leads to a drop in total internal moisture. So on the left we see on a warm winter day, on the right we have a cold winter day. The difference in total moisture is solely due to the external moisture levels, and this can significantly influence the internal levels. And remember, the differential vapour pressure, that's the difference between internal minus external, reflects the internal moisture production only. We also note that the internal vapour pressures are very dependent or related to the external vapour pressures. The external vapour pressure is a major driving force. Thus, if the external vapour pressure goes up, then so will the internal vapour pressure. Conversely, if the external vapour pressure goes down, so will the internal vapour. That will drop as well. So to summarise, vapour pressure directly reflects the amount of atmospheric moisture. It is not temperature dependent. Thus, for a given level of water vapour in the air by weight, the vapour pressure will remain the same, irrespective of temperature. The internal moisture vapour level is made up of the sum of the external vapour levels plus internally generated vapour from occupation activities. The internal vapour pressure is influenced by the external vapour pressure, and on average there is more water vapour in the internal air than external air during the colder months of the year. The difference between the two is known as the differential or excess vapour pressure.